Okay. Well, welcome to Thursday. I still don't have a classroom for our test, but I think I've got a line on one. So you'll get an email this weekend, hopefully tomorrow, today or tomorrow, about where the exam will be. It will be in person. You'll need an FE approved calculator, pencil, and that should be about it. If you want to bring some spare paper, that might be a good thing, just in case you're like, Dr. Wagner didn't leave me enough space. Okay. You can always pull out paper. That should be about it. Okay. Before I begin, I did want to say something about homework. I'm getting so many emails about homework. Some of you guys are really, really, really stressing about homework grades. Part of the reason that I've done homework the way that I did it was hopefully so that there wouldn't be so much stress about homework grades. And you guys are overpowering all of my attempts to de-stressify homework. So I tried to make it less stressful by making it worth only 10% of the grade. I tried to make it less stressful by I don't really have an official policy on this, but I will drop at least 2 homework grades, but usually ends up being like 3 or 4. I've tried to make it less stressful by over IDA, basically giving you no deadline for that one assignment that was due over that time. I try to make it less stressful by all of the Connect stuff. There's only a 10% penalty per day if you're late. And yet through all of this, every day I come in and I try to, I'm like, all right, I'm gonna get to work, I'm gonna start grading. And then I'm just answering questions about people basically asking for homework points. Email after email after email after email. And I don't blame you. I know you want your points, but there's clearly just a lot of stress about this. So before I do actual class here, I just wanted to show you something real quick. I'm going to share my screen. Come on, you can do it. I got it. Can you show me my, okay, so hopefully, hold on. Rocky! Shh, stop. Hey, you're all right. Stop. No. I'm working. You don't need to bark at stuff. Okay, so let me give you an example here. Where did it go? Oh, here we go. All right, this is from a random semester. This semester is actually fairly recently, but I won't tell you what class it is, whether it's statics or fluid mechanics. In fact, I don't even know because I've forgotten. This is how I calculate your final grade. Okay, you see there's a homework column. I'm scrolling over so that you can't see the names. But you see there's a homework column, there's a test column, and then there's an overall average. Okay, look at the overall average and compare it to the test average. Okay, now you'll notice this semester I had some really, about half or 2/3 of the class disappeared. So that's why everything is highlighted in red. So that's how I determine your grade, is by what color the computer highlights you. So like that person at the top, their overall average was an 80. So they're highlighted in green. I didn't make any decisions. I just enter the grades in the computer, and then it will highlight you based on what your grade is. So the middle column is the overall average, and then the left column is homework, and the next column is tests. And if you look down that, look at how the test grade and the overall average, look how they're basically the same. Okay. And look for people whose homework average actually bumped them up or down a grade. Extremely rare. Okay. It's extremely rare for your homework grade to really matter. All the way down at the bottom, there was somebody who had a 90 homework average, had a 70 test average, and they got a C. And that, bumped them up 2 points. Okay. It's not important really. Okay. And I'm not saying homework is not important, but your homework grade is not important. Okay. Now you will also, since we're here and we're staring at this, you'll notice the exam score, so the exam score goes into that test average, but then also if your exam score is higher than your overall average, and your exam score counts for your final grade. So you'll notice that first person at the top of this particular class who had a B average all semester, they got a 96 on the final. And so they got a 96 in the class. Okay, even though their overall average was an 80. Okay, and so that's on offer to you guys too. I do that in all of my classes. That's just something that, or like, about halfway down, there was somebody who had an 87 overall average. We got a 97 on the exam. And so got a 97 in the class, And what you'll notice, of course, the other thing you'll notice is that the people who get those really high grades, most of them have really high homework averages. And it's not because, because they begged me for points that they got those 90, that they were able to get those really high scores. It was because, they worked really hard at the homework. It's about the work that you put in on the homework. It's not about the grade. Okay. And I need that to be clear. Okay. I want you all to not stress so much if possible. Now, I mean, obviously, by all means, keep asking me if you think you've been wronged. By all means, let's get it righted. I'm always willing to right the wrongs. But when you forget a homework date or something, don't stress out about it. I still highly recommend you do the homework. And I've structured the late penalties on Connect to be like, hey, look, you're within 10 days. There's still a value to it, point wise. But really, you should do it so that you learn the material. Okay, because ideally, you can be one of these people whose exam score is an A, and you get an A in the class, even though maybe your homework average for the semester was in the 60s or the 70s. Totally fine. That's like very typical. That's my expectation for most of you, is to have a homework average in the 60s, 70s, maybe at best in the 80s. It's very rare for me to have somebody have a homework average in the 90s. Okay, and it looks like somebody in this class down there at the bottom had a homework average in the 90s. But yeah, so what I'm saying is, let's take care of business, but take care of business in the sense of, let's learn what you need to learn from each assignment, right? I'm picking problems that I think will teach you something. I'm not just giving you busy work so that you can get some points. Okay, if you want, I could just give you I've considered just making homework worth nothing. And so essentially just giving you all the points, but then no one would do the homework, right? So it's just really, it's impossible for me to figure out how to do this correctly. But I think we're losing focus on what the point of the homework is. So again, if you need the points, if I've somehow messed up and I owe you points, by all means, let me know. But please don't stress out about it. It's not worth that much. Okay. So like, even if you were to like look at these homeworks, you're like, oh wait, but look, about 2/3 of the way down, there's someone who had a 88 homework average and they had a 79 test average. And that 88 pulled them up to an 80, and they were able to they should have had a B for the class, except they aced the final. So if you see that person, that column, it's 88, 79, 80, 90, 90. Well, they aced the final because that 88 homework average, they were clearly working really hard on the material. But let's suppose I didn't have that thing for the final, or let's suppose I didn't do all that well in the final. And you're like, well, look, it bumped them. Yes, it did. But a couple of homework points here or there wouldn't have made the difference between that going up or down. It was the fact that it was really just that the 88 it was really that they were on the bubble, and that 88 was high enough relative to that 79 to bump them. So anyway, play with the numbers if you want, your own numbers. Obviously you can't play with mine. So anyway, just something that, is kind of, affecting my, where are we? Where's my Zoom? Here we go. Okay, so I'm going to stop share and I'm going to actually teach and not talk about that anymore. Any questions about that? Okay, I mean, I know that I'm probably not going to convince you. Some of you, it's been so hardwired into us, that, people always say, well, homework is the most important thing. And it's really what they should say is it's what you learn from homework that's the most important thing. And of course in high school, and I won't say that there aren't college professors this way, there are college professors this way who basically say, look, if somebody does the homework, I'll bump them. I'm not going to bump you because you did the homework. I want you to learn the material. I only care about the material. Okay. All right, reactions. All right, so what we're going to do here, hold on, I want to be able to see you guys if I can. Okay. So what we're going to do here is we're talking about reactions, and yeah, and so a reaction is something. So basically, what a reaction is it's like how does something, a frame, usually just a frame of some sort. It could be a truss, it could be just a frame, it could be anything. And so the reaction is basically, what does the rest of the world have to do to support our frame? Okay, so what kind of moments, what kind of forces does it need to keep something going? And so to talk about reactions, the first thing we need to do, and actually I wrote all this down so that I wouldn't forget any, is that we need to think about the ways that our frame or our truss or whatever it might be, how it connects to the world. Okay, so there are types of connections. Okay, and it's basically, how does the world connect to these things? How does your frame connect to the world? Okay, and basically there's three types. Okay, and you're going to write them down now, but you're going to internalize all of this, just as I did, because it's just going to like show up all over the place. And let's see, okay, I'm going to go to the strongest to the weakest, I guess. Okay, so the strongest is the cantilever. Okay, or I guess, I would call it the cantilever. And so what it boils down to is, it's like, it's usually horizontal or vertical. It doesn't have to be. But what it looks like is it looks like this. This is how it's always drawn. Okay, and the right-hand side goes off and does whatever it does. But I'm concerned with this left-hand side. Okay, and it's drawn like that, or it's drawn like this. Okay, and again, there could be stuff up there on the top. I'm not really worried about the top in this case. I'm worried about the bottom. And so when you draw a free body diagram of that thing, what you have to think about, and this is really the easiest way to think about it, is you say to yourself, okay, what kind of forces can the environment put on that cantilever? So if I were to draw the free body diagram of this thing, okay, so I'm going to cut off the world, and I want to think about what forces, let's say this is point, I don't know, H, I don't know, we'll just give it a letter. We'll call this point I. Anyway, it doesn't matter. So when I've got this point H, I want to think about, well, what happens if this particular beam, like if I were to try to move it up or down, could this environment push back? And the answer in this case is yes. Like, let's think about this. Let's think about the one on the right first, actually. I'm going to cut away the rest of the world. I'm going to do my free body diagram. And, so let's suppose you're walking down the street, you see this pole sticking out of the ground, and it's buried in there or whatever. And so it's kind of cantilevered like this. And so you say, well, okay, if I push against the bottom of that pole, will it push back? And the answer is yes. So I know that there's a force right here, or there potentially is a force right here. Okay. And we'll call that force I in the X direction. Okay, and then I'll ask a second question. I'll say, what if I walked up to that thing and I tried to pull it up? It's like I tried to pull it out of the ground. Will it resist that? Or tried to push it down into the ground? Will it resist that? And the answer is yes, it can have a force in that direction. Oh, I should note that these are all 2D. Okay, we'll talk about 3D drawings of these in a bit. Okay, so then the last question I want to know is, will this thing resist a moment? So what happens if I twist it? So if I went down to point I and I just I put a screwdriver in at point I, in the Z direction, so in or out of the board, and I tried to twist it somehow, would it resist that? And the answer is yes, it would. Okay, so that means we've got a moment. Okay, so I'll call that moment at I, a moment at I. Okay. Now, what I'm going to recommend in general is, in a problem, is if you don't know the directions of the forces that you're assuming, is that you just assume them to be positive. That's generally a preferred way to do it. I'm going to recommend you do that again and again and again. Okay. So, so that would be, the cantilever on the right. The one on the left, it's the same sort of thing. So if you imagine I went up to point H and I just started pushing at the bottom of that thing and I started pushing up, so here we go. I'm like pushing, or like I'm pushing down, whatever. Could it resist? And the answer is yes. Okay. It's not going to easily move from that position. I'm trying to think of a case where you've got like a, something that looks like this, a cantilever like this, but, And so kind of what you can do here is once you notice you've got a cantilever, you know that this thing is like solidly in that wall, right? So you can go, oh, okay, well, it's gonna look like this. Okay, like if I push on this particular thing and I push this way, or if I push this way, that wall can push back. Okay, so that's gonna be HX. Okay, and again, like if I walk up to that thing and I just start twisting it either this way or this way, it can resist. Okay, it's not just going to start twisting freely. So what I'm going to do is I'm going to create a moment in H. Okay, and that moment is being caused by the wall. Right, the wall is resisting my my motion. Okay, and now I'm seeing why I should have done this in the opposite order. I should have gone from most or least restrictive to most. Okay, so that's the cantilever. Okay, any questions on that?
Okay, so you saying like when is can you hear me?
Yep.
Okay, so like the moments, is that like twisting it? That's not like rotating it like around the axis, is like actually trying to like twist the pole.
So the moment, the MH or the MI is actually the ground preventing it from twisting.
Like so if you twisted the one on the right, it would look like if you twisted the one on the right to the right, it would look like the one on the left.
No, these are unrelated.
Oh,
okay, so if I were here and I were to go up to this thing and I were to twist it this way, right? I were to apply a moment to try, oh, not, sorry. Come on, you can erase, you can do it. Why won't, okay, there you go. So if I went up to the one on the right and I said, okay, I'm gonna like start twisting on it like this, okay, the ground essentially is gonna resist that by applying a moment onto, by like doing an equal and opposite moment. Okay.
okay.
If it can't resist it, then the pole is just going to twist over.
Okay.
We'll have a failure. So maybe it's raining or something, and it it just can't support that kind of moment.
I see what's going on.
Okay. So so any other questions? Okay. The next one is usually called a pin connection, and a pin looks like this. Let's see. There's a few different ways that you can draw it. The most common looks something like this. Well, let's see. Let me draw one relative to the environment and not an interior one. Usually you draw it like this. And then you've got you've got a frame piece going this way. Again, I'm not worried about the rest of the frame. I'm just worried about this. And what you do is you draw the pin like this. Okay, now again, this could be horizontal, vertical, whatever. It could be over here, with the frame going this way, maybe, whatever the case may be. Okay, and what we're showing here is that the frame, or that particular member of the frame is connected through this pin. So you just kind of like nail something through the middle. Okay, and again, what we want to think about is it's like, okay, well, let's do the free body diagram. Okay, so here's my pin, or here's my frame. Okay, again, I'm not worried about what's going on up and to the right, so I'm just going to kind of like cut that off. There is something over there. I just, I'm just not concerned. I'm not concerned with that right now. And so we're thinking about, like, let's suppose, I went up here and I pushed up or down on it. Could that pin resist it? The answer is yes. Like it's the fact I put that pin in there specifically to keep it from going up and down. That's one of the things that I did. So, I don't know what we call this point, HI, we'll call this point J. So I've got a J in the Y. Okay. If I decided to go over there and push it left or right, okay, will that pin resist that? Will it try to keep it in the same X position? The answer is yes. It's got a position, so this is going to be JX. Now, again, if you can't figure out the sign, I always just assume positive, okay? And then the last thing that you'll want to do is you'll say, well, what happens if I go up here and I start twisting it? Will that pin resist that? And the answer is no, it will not. Okay, now obviously, we're assuming some sort of frictionless pin. So if the pin is frictionless, then it will not resist that. So the pin itself does not apply a moment to that frame, no matter what. Okay, and that's the same thing over here. So every time you see a pin connection, you just go, okay, like, so if I do this one, the free body diagram looks like this. Okay, and then we just go, okay, well, let's, just like right off the bat, you can say, well, JY or J, K, this will be KY and KX. Okay, so KY and KX. Okay, and in no way, shape, or form will you ever find a case where this thing can suddenly, yep.
Hey, Wayne,
Yep.
for purposes of this example, do we worry about the bracket attached to the wall? Like forces being transferred through the bolt or pin to the wall? Or are you just focusing just right now on the hinge?
We're just focusing on how the hinge is supporting the rest of the frame.
Okay.
Okay. Yeah. If you were asking a question about the bracket, then the wall on the bracket can support a moment, but it can't but that moment cannot be transferred to the frame because it's going through a pin.
Makes sense.
Okay. Okay. So this is, this is pretty straightforward. The pins can be written a lot of different ways, and not the pins. The pins are pretty straightforward. It's the last one that we're going to do that can be kind of strange. And so the last one is the roller. Okay, so let's see here. And rollers can be written a lot of different ways. And hopefully I can remember them all. Or, here's 3. Let's see if we can do the roller. Okay, and it looks like a wheel. Okay, so usually you'll write it, let's say, this is like the most common. Okay, and then you've kind of got this is a very common way. Okay, so you've got some sort of like, frame or whatever, and it looks like it's sitting on a wheel. Okay, you will also see that drawn like this. Let's see, so I'm going to draw a few of these. Sometimes you'll see it like this. Let's see. You will see it. Sometimes it'll look like a little rocker. Let's see, I really hate when they do the rocker. I mean, it doesn't really matter. The key is that when you see it, you go, oh, I see what's going on here. And usually, the bottom is almost always drawn, with these diagonal lines to let you know that that's what's going on. Okay. And again, in this case, what you have to think about is, okay, if I walk up to that thing and if I want to draw a free body diagram, so then what I'm going to do, I mean, all of these are the same draw. They're different looks of the same drawing. So here's my free body diagram. Okay, and I want to look at it, and hopefully you're already thinking that you understand what I'm saying here, is that if you push on this thing up or down, well, it's going to resist. Okay, now rollers as drawn, really only push up. But a lot of times there are problems where they'll say something like, this roller is on a track and the track is keeping it from, like if you imagine, so I found a really good problem yesterday. I was just kind of flipping through, I think it was in your textbook. I can't remember. I find problems in so many different places. And it was like a garage door opener. And so you can imagine a garage door opens kind of got a wheel, and the wheel, the wheel, and when it's going vertical, the wheel is keeping it from moving left and right. And of course, garage door opener is a little bit special because it actually, depends on if it has a motor or not, but the wheel itself might prevent it from moving up or down. But in this case, if we were to think about, okay, so if I push down on this, can it resist that? And the answer is, well, yeah, it's going to push back, right? It's going to have a normal force going up, HIJKL, so we'll call this point L. So we would just automatically give it an L in the Y. Okay, if I push it left and right, can that wheel prevent it from going left or right? And the answer is no. Like you went and pushed on something that's on wheels, it's just going to roll away. Okay, so it can't really do left or right. And if you tried to twist something that's on the wheels, like if you went up to it and you were like, well, I want to lift this side up, so I'm just going to twist it like this. Okay, well, it's not going to resist that either. Okay, so, so it's like, what can the wheel do to the frame? Okay, and that's really, these are the types of connections. The only other types of connections really are like ropes. And anytime you have a rope or a cable or something like that, those are actually really nice connections because you know the direction the force is going. A rope can only pull. I say that because, my first example is a rope problem. So yeah, any questions about this before I get to some examples? Okay, so
Yeah.
Go ahead.
So the roller, no force in the X direction.
No force in the X direction.
Okay.
Unless the roller is oriented vertically.
And then what about, so the pin also has no moment because it's freely swinging about that pin.
Yeah, that's actually the correct term for it is freely. I don't know if it's freely swinging, but freely moving or freely rotating, I guess would probably be the best term for it.
Okay, cool.
Okay, yeah. So, and that's really what you always want to think about. It's like, I mean, obviously, in the real world, there's friction and things like that. So there's nothing perfect like this. I don't know how often we design things with rollers in like static things with rollers. I think a lot of times we use rollers in statics class because we haven't learned more structural analysis. And if we don't use a roller, then we can't solve. I'll make that clear as we go. So here, I'm going to clear all my drawings. And then I'm going to do an example problem. I did this one on an exam last year. And so actually, you know what? This one's definitely out of your textbook. I had it open to it. Oh yeah, there it is. Okay, so it's a bit of an annoying problem because it's just got a lot of forces, but it's probably wasn't a good one for an exam because it took too long. So there's a frame element here. If you want to look for it in your textbook, it's 4.4 out of your text. And basically, let's see here. So I'm going to kind of try to draw it the way they've drawn it. Let's see, this is point B, this is point C, this here is point A. Okay, so we got 15 pounds. £5. Okay, so it's going to be, it's a very unusual thing. I'm trying to imagine something this small having this much weight on it. Okay, and what is it that we're looking for? Oh, it says solve for the reactions. Okay, determine, so I guess, so that's given. And the required is we want reaction at A. So I want A, X equals what? A, Y equals what? So when they ask for the reactions, usually we say A, X, A, Y. Because this is a pin, so I'm not going to solve for the moment at A because, we're not worried about that. And then it wants the tension in BC. Anybody want to tell me how to solve this? What the first step is?
Sum of forces.
There's something we always do before sum of forces. But that is the correct answer. Okay, so the first thing we always, if you're going to sum forces in my classes, anytime you sum forces, you have to draw a free body diagram. Okay, the thing you're summing forces on. Okay, otherwise, I'm not even 100% sure what that means. So what I'm going to do is I'm going to go up to this thing and I'm going to say like, okay, so this is what I'm drawing the free body diagram of. So I've got this red line. Okay, so now that I've done that, I need to think about all the, so they didn't tell us anything about weight. So that's the only force that doesn't cross that line would be a weight. Okay, that's a body force. All the other forces are surface forces. So all the other forces are things that I've cut away by, deciding that that was my, that this is my free body diagram. So I've got, I've got 15 pounds here. I've got 20 pounds here. I've got 35 pounds here. I've got 20 pounds here. And I've got 15 pounds here. Okay. I also cut away the world at A. So I've got two forces at A because it's a pin connection. So I've got AY and I've got AX. Okay. And I also cut the rope from B to C. And the nice thing about that is I know that that thing is going downwards. Okay. So TBC. Okay. Note, I don't know which way AX and AY are going. It seems kind of likely that AY is going to be up because we have so many downward forces. In fact, it's really hard to imagine anything else happening. But AX, I don't know. So, but I mean, I didn't even think about it. I just automatically make them positive. You will find other people do it differently. But what happens is when you solve these, if you get a negative number, that means you drew the arrow in the wrong direction. Okay. So you're right. We're going to sum forces. Okay. And basically, this is a two-dimensional statics problem. So when you do this, we know that this thing is not moving. And so we know that the sum of the forces in the X equals 0, the sum of forces in the Y equals 0, and the sum of the forces in the, the sum of the moments in the Z direction around a certain point are 0. Or really around any point. Okay, so in the X direction, well, this is really nice. So I'm going to expand this term. Okay, I only have one force in the X direction, that's AX. Okay, I'm going to leave the right-hand side alone. So there you go. I've already solved for one answer. AX equals 0. Okay. Now I'm going to do the Y direction. Sum of the forces in the Y direction equals 0. Okay, I'm going to expand this. Okay, and look, this is a little annoying, but I've got negative 15, minus 20, minus 35, minus 20, minus 15. Whew, super annoying, right? All those forces on the top. And then I've drawn AY up, so I'm going to call it a plus AY. And I drew TBC down, so I'm going to do minus TBC equals 0. Okay, you'll note that we can't solve that yet, right? It's two unknowns, one equation, can't be solved. 15 plus 20 is 35, plus another 35 is 70, plus 20 is 90, plus 15 is 105. So we'll say, let's see, AY equals TBC plus 105 pounds.
Wayne?
Yeah.
So my intuition would be to add these perpendicular forces or these perpendicular distances to these weights. Why wouldn't you do that?
Oh, do you mean for what do you mean? You mean
like 15 pounds, well, minus 20 pounds times 6 or whatever.
Oh, okay. Well, we will do that, but that comes to effect with the moment equation.
Oh, okay. Okay.
Okay. So, and this is where we're going to start thinking about moments. And there is some magic, maybe not magic, magic is the wrong word, but there is some intelligence that comes with where you pick your moment to be. Okay. So we can pick a moment anywhere on this thing. We can even pick it off of this thing if we wanted to. Like I could take a moment around a random point up here if I wanted to. Okay. And what's going to happen is the sum of the moments is still going to be 0. Okay. The sum of the moments has to be 0 everywhere on this frame. What do you think is obviously doing it up here seems a little bit difficult, like a little bit, annoying and like not really the way that we want to go. Anybody have an idea what the best point is for doing a moment on this problem might be?
My first thought about looking at is the pin or the rope connection.
Okay, so either here at A,
Where wants to pivot naturally.
yes.
Yeah.
A lot of times where it pivots naturally is a very good way to do it. I like that location, at A in this case. I like that location a lot because it's logical to me. But really A or B is your best choice. And it's all about math, really. And it's about how many forces we've got. Well, we've got 1, 2, 3, 4, 5, 6, 7, 8 forces, right? And so this is an annoying problem, right? There's a lot of different forces. So I want to pick a point that the line of action of as many forces as possible goes through that point. So if you'll notice, like if I pick A, for example, AX goes right through the middle of that. This 20 pound goes right through the middle of that. And this AY goes right through the middle of that. So all of those have no moment arm at A. Okay. If I choose B, for example, let me do some blue. Okay. The TBC goes through the middle of it. So it has no moment arm. It causes no rotation around B. Okay. This 15 pounds goes right through the middle of it. So it causes no rotation around B. And this AX, which of course doesn't matter in this case because it's 0, but just kind of in general, it goes right through the middle of point B, so it has no moment arm either. Okay, so that's 3 numbers or three forces I don't have to calculate in my moment. Okay, if I just picked a random point, like if I did it out here, I don't have to worry about this 15 pounder, and I don't have to worry about AX, but I have to worry about all the others. So that would be a second best, would be to do it at any one of these other forces. And the worst point would be to just pick a random point somewhere in the middle. Okay, or worse, off of the thing entirely. Okay, so just something to kind of keep in mind. Okay, so I'm going to choose point A. The 2 best points would have been A or B. So you were right with that. And so we're going to do kind of exactly what you were just discussing. So we'll start. We're going to do the 15 pounds. Okay, and its distance away is 8 inches, 8 inches, 6 inches. So that's 16, 22 inches. Okay, that is causing things to spin around A. What is that? That's counterclockwise, so a bit of a positive sign. Okay. Notice I'm keeping this in inches because I don't feel like converting. Okay. Like this basically means all of our moments are going to be calculated in inches pounds instead of foot pounds, which is a little bit annoying, but we can convert it later. So, but you just got to be careful if you decide to do that. Okay, so this 20 is going to be the same direction. This 35 is going to be the same direction. So we're going to do plus 20 pounds. It's perpendicular distance. Remember, we're talking about distances that are perpendicular. So this 22 inches perpendicular to that force. Okay, this 20 pounds, it's up, down. So we need a left-right distance of 16 inches. Okay, this 35 pound. Okay, perpendicular distance.
Wait, why is it only 16 inches?
Because we're going from A to this point right here for that 20 pound force. So it's 8 inches to here and then another 8 inches to here.
Okay, thank you.
Okay. All right. So then when we get to this 20 pounder, okay, it's got a moment arm of 0 because it's going right through our point. AY has a moment arm of 0 because it's going right through our point. AX has a moment arm of 0 because it's going right through our point. So we like all of that. That makes us happy. And then we've got to get this 15 pounder here. Okay. And it relative to our point, causing things to spin this way. So that's going to be a negative minus. And I could make this 15 pounds plus TBC because they both have the same moment arm. But I'm just going to kind of keep them separate for now. That's 6 inches. Okay, and then we're going to do the minus TBC, also times 6 inches equals 0. Okay, so at this point, you should see that this is just a math problem, right? We're gonna solve for TBC here, and then once we have that, we will plug it in right here. Okay. So let's go ahead and I'll solve for TBC relatively quickly. Notice because it's all in inches, the inches are going to cancel out when I do the division. So 15 times 22 plus 20 times 16 plus 35 times 8 minus 15 times 6 equals, and we'll divide that by 6. Okay. If this were on a test, I would recommend that you would plug that into your calculator twice, just because there's points involved and whatnot. Okay. And so then if I were to go back and solve, that top equation, I could then say, well, AY is TBC plus 105. So this is going to be what, 250, 245. Okay. And sometimes, if I ask you for a direction, like if I say, well, TBC, let's suppose I said, I wanted the arrow, so if I gave you the arrow on top, what you would do is you would say, okay, well, TBC equals 140 pounds down. Okay. Or you could say TBC equals, now this would be annoying, but 140 at an angle of -90. Ooh, that sucks. Don't like that very much. And then for AY, you would I guess you would do the same thing. AY, it turns out, is positive. So you'd say, well, AY equals 245 pounds up, or AY equals 245 pounds at an angle of 90 degrees, right? So just a few different options for how you report. It depends on whether or not somebody wants the magnitude of the force, or if they want the, so just, when I ask a question, make sure to note whether or not it has these things.
When?
Yeah.
So I kind of lost a little bit on the TBC and the AY with your directions. How do you can determine that? Is that just numerically one's positive or negative, or how do you determine direction?
Oh, so the way I determine direction, and I guess I could solve this twice, is right at the beginning of the problem, I assumed AY was positive. So and I assumed TBC was negative or downwards. And so what I did is over here, when I plugged them into the equation over here, I assumed AY was positive by giving it upwards by giving it a positive sign. I assumed TBC was downwards by giving it a negative sign. And then when I did my moments, I'm assuming TBC was downwards. So I, gave it a direction, a sign commensurate with that direction. If at the end, if I'd gotten a number, let's imagine I'd gotten a number and TBC had been negative. That would have meant I assumed the wrong direction for TBC.
Got it.
Okay. And the trick here is, like some people will tell you to try to figure out what direction the force is going beforehand and assume that direction. That's fine. I'm okay with you doing that. But I like to always assume positive unless it's a tension. And that way, when it gives me an answer and I get a negative sign, that just means it's downwards. But if you assume it's downwards and you get a negative sign, that means it's upwards. So, how confusing is that? Not too confusing, but when you're doing 10,000 things and you've got 100,000 calculations that you're working on, whatever you can do to make things simpler. To me is beneficial. So let's do another one. Okay, so good questions, great questions, guys. Y'all are crushing it. Like I'm enjoying y'all. This is really quite wonderful. All right. So this one's what did I like about? Oh, this one's different because it's just got a few more things going on. Okay, so we've got by the way, so we're going to do 3 examples today, and then I should really give you all copies of these so you can see the many different drawings of pins and whatever, cantilevers and things like that. Okay, so here we go. Okay, we've got a weight right here. This is point C. The weight is 150 newtons. Okay, so then this one I thought I really liked because I've just never seen one like this before. And I thought this was pretty cool. So this is point B, this is point C. And this thing is going up like this.
Wayne.
Yeah.
So like at point C, if you don't specify a distance to the very tip of it, we would just assume that that weight is suspended from the very tip.
Yeah, but I mean, you'll have a distance. I mean, unless the point of the question is to solve for the distance.
Okay.
You should always have distances.
Okay.
Like what I'm drawing right now, like this is, let's see, this is 3 meters. This is 5 meters.
Well, I'm talking about to the right of that weight.
Oh, like this little bit right here. Yeah, I don't want that.
Okay.
I've never seen somebody try to, I've never seen somebody try to sneaky on that. I guess it could happen, right? I don't want to, I don't want to tell you what your other professors might do. Okay, so go.
C's on here?
What's that?
Do we have 2 C's on here?
Oh, we do. What did I do here? Oh, that's interesting. Good point. For some reason they didn't, you know what? I'm going to use my own letters because this is silly. Like, why would that? This should be, let's see, A, B, C. Let's make this D. And this point up here will make E. Sorry. Yeah, thank you. That's really strange.
Thank you.
The original drawing only marked 4 of the 5 points. And so I accidentally gave a C where there shouldn't have been something. Anyway, but thank you. Okay, so what they want to know here, this is given. And then the required is, let's see, determine the tension in the cable. So tension equals what? Okay, and then this is a pulley, by the way, up here at the top. That's a pulley. Oh, come on. Well, I can't write the word pulley because it's too close to the top. So please bear with me. PUL means pulley. So we want the tension in the rope. And then we want, the reaction at A. Okay, so I'll write it like this. Okay, I'll put an arrow on the top so we can go with that. Okay, you should actually, to some extent, you should already be able to tell which direction AY is going. And you should actually be able to tell which direction AX is going in. Can anybody tell me right off the bat which way these are going without doing any work at all? Does anybody have a guess?
First I was going to swing down because the weight on the end, but then will the pulley counter that with the length on the rope? So my first guess is swing down, but it might be not that much because of the pulley and rope.
So you think AX or AY? Which one are you talking about?
Oh, I was looking at D, way over in D. So AY, the whole arm should go down. So clockwise, wherever that would be.
Okay. Well, there can't be any clockwise because it's the pin, so it can't support a moment. So anyway,
Say down.
okay. So the guess is down. Okay. So
AY would go up.
and I'm going to draw a free body diagram because we know we're summing forces in moments. So you always need to draw a free body diagram. Now, a lot of time in statics class, especially for the reactions, we just do the free body diagram on the initial drawing. I don't particularly like that very much, especially, not because it can work just fine, but for students who are beginning, there's just like a lot of stuff that kind of gets lost in the weeds when you do that. So
And do you want the tension in the rope on the weight or in the EBEC?
Well, the rope on the weight is pretty straightforward. It's 150 newtons.
Yeah. Oh, okay.
Yeah, so I want the tension in the rope. Let's see, what do they call it? They call it the tension in the cable.
And then EB would equal EC, correct?
Yeah, EB will equal EC, right? And that's why I just use one letter T. And so for this one, because it doesn't have, for the tension, I don't have any markings on it. So we're just going to go for the magnitude of the tension. And then for the other one, we've got, but for A, we're going to look for the vector itself. So here's my free body diagram. Again, like I've cut away the rest of the world. Okay, they didn't tell us anything about the weight of this beam. By the way, if they ask you for the weight of the beam, for now, just assume the beam is like evenly distributed weight and apply the weight at the midpoint. Okay, so in this case, if this thing is 13 meters long, so you would apply it 6.5 meters from A, 6.5 meters from C, and you would just put a downward force where that weight is. Okay, it's not really quite that simple, but we'll get to that, or we won't. But it'll show up, in your structures classes. Okay, so then we've got a force C, and it's going to come off like here. Okay, and that's gonna be a tension. We're gonna get a tension right here. All right. And then for AX and AY, what I always tell people is assume positive. Okay, right now already, if you're looking at that thing, you should be able to tell that AX is going to be positive. Because if you're thinking in terms of X forces, we've only got one force in the X direction, and that's one tension pulling back towards the wall. So this thing has to push back the other way. I'm going to go ahead and assume the wrong direction. Okay, just so that we can see how this will work out if we choose the wrong direction. Okay, and then, you know, from the moment standpoint, well, it doesn't matter. I'm gonna assume both of these are negative. The AY is gonna end up being the correct direction, but let's just go ahead and we're gonna roll with it. Okay, so before I even get into some forces in the X and the Y, I kind of want to get at this little tension, the X and the Y components of this guy right here, because I don't particularly want to deal with, you know, I mean, I could do sines and cosines. So what most of you guys would do is most of you guys would try to find this angle right here, and then you would do sines and cosines. I would note that this angle, this is a square root of 5, so that we can just kind of work with you know, similar triangles. Let's do it the way that most of you guys would do it. Let's find this angle. So that angle is going to be the inverse tangent of 2 over 1. Inverse tangent of 2, essentially. Okay, 63.435. 63.435. Okay, so that means this one right here is going to be T sine of 63.435. And this one right here will be T cosine 63.435. Okay, I would be more inclined, if I was doing it, to say that this would be T of times 1 over the square root of 5. And this would be T times 2 over the square root of 5. Okay, it's kind of whatever you want to do. So if I type in 2 divided by square root of 5, I get 0.8944. Okay, and if I do sine of 63.435, I get the exact same number. Okay, so it's kind of whichever way you want to do it. Okay, this is the unit vector, and this is just the trig function. So it's whichever way you want to do it. Okay, it's not very ugly 63. This is not designed for teaching classes. That's clear. Okay, so now we're ready to roll. Okay, and I'm assuming negative over here. I don't recommend that, but we're just going to go ahead and do it. Okay, so sum of the forces in the X direction equals 0. We know this thing is static. Okay, so that's the way it goes. Now, if I don't know what I'm doing, I would just go in order. I go sum of forces X equals 0, sum of forces Y equals 0, sum of the moments around some point equals 0. What I recommend to you is, yeah, so if you don't know what you're doing, just do X, Y, and then moments. If there's something specific you're looking for, it helps to think about the equations before you begin, so that you can like visualize which one you're going to work with, so that you don't have to do all this extra work. Okay, the X direction is really easy in this case. A lot of times the X direction is. Obviously, I can give you a problem where the X direction isn't. So in this case, I've got AX, which is negative because I assumed it was negative. Okay, and then I've got the X component of the tension in that particular rope right there. So minus T, I'll use the cosine of 63.435 degrees. Okay, equals 0.
So I would have assumed AX is positive. Would that have messed up anything?
No, like yeah. So looking at the diagram, I can tell you AX is going to be positive. I'm intentionally making this quote unquote error, right? So if you assume the wrong direction, what happens is what I'm going to show you. If you assumed that, when this is over, I'll go back and I'll show you what will happen by just I'll just change that AX as I've drawn it, and I'll change it the other way, but you'll see it won't matter. You'll still get the right answer. Okay,
Great, thanks.
okay. I'm gonna leave a little space under that one in case I want to come back and solve it. So I'm gonna do sum of the forces in the y equals 0. And of course, we have a few more of those. I assumed AY was negative. I'm pretty sure actually this one will end up being correct. So it's actually kind of nice, like I made them both negative just because I wanted to show you what would happen. And I think in this case, one will be correct and one will be incorrect. Anyway, so we got AY going down. I've got a T going up. Okay, I've got another T going up, but this is the angled T, right? T sine of 63.435 degrees. Isn't it annoying that Dr. Wagner makes us keep 5 sig figs until the end? Let's see here, 435 degrees. Okay, oh, and then I've got this 150 newtons, which I forgot to draw. Okay, so then I've got minus 150. Okay, so can't solve either one of these, right? 2 equations, 2 unknowns for both of these. Well, that's annoying, right? So I can't solve either one of these. And I could simplify them, but I've kind of chosen to let's wait a second. Okay, so then the last thing is going to do sum of moments. Okay, in the z direction. Okay, I didn't even define a coordinate system, but generally, if this is x, this is y, so this is z is going counterclockwise. Okay, and actually, usually you want to do that on your free body diagram. I always forget. And so again, where somebody just hollered out, where do you think I want to take my moment?
Hey,
Hey,
A, right? Because then we don't have to worry about AY and we don't have to worry about AX because both of those go through that point, right? So if I take my moment here, okay, I've got no perpendicular distance for AX and AY and one other kind of force. What's the other thing that I won't have to worry about? Oh, I
don't know.
Okay, so the other thing that we won't have to worry about is the X component of this tension. Okay, because you can see, if you look at the line of action, just keeps going, and it goes right through there. Okay, so we don't have to worry about the X component of that force. Okay, so that's always nice. Okay, so this equals 0. So I'm going to expand this one. Okay, yeah, so note, by the way, I'm always expanding the left-hand side of this thing. A lot of people like to do really weird things and it creates problems. So always work downwards. Okay, so I'm starting at this point at A, and notice AX goes right through the middle of it, AY goes right through the middle of it. So don't worry about those. And so I'm just going to go to T. So T is going up and it's causing things around A to go counterclockwise. So it's going to have a positive sign. And its moment arm is 5 meters. Okay. Then I'm going to go to the angled force. And again, like I said, this one we don't have to worry about because doesn't have a moment arm. It just goes right through point A. But we do have to worry about the vertical one, right? So and that's causing things to go counterclockwise. So we're going to go plus T sine 63.435 degrees. Okay, times its moment arm, which is what, 10 meters. Okay, it's always good to step back at some point and go, wait, did I get the moment arms right? Because, did I remember them? Because, it happens. And then we got this 150, which of course is causing it to spin the opposite direction around A. So I'll go minus 150 newtons times its moment arm, which is basically the full thing, 13 meters. It equals 0. Okay, questions about how I got that equation? Because after this, it's just algebra. And when I grade your exam, this is most of the points are, can you get these equations? Okay, solving the equations, if it's a 10-point problem, solving the equations at most would be 4 points, but usually it's 2 points. I guess it kind of depends, but most of the points are just get these equations. Okay, so I'm gonna go ahead and I'm gonna solve this as quickly and prettily as I can. So we'll say T times 5 meters plus 10 meters sine 63.435 equals, I'm bringing the 15 times 150 times 13 over to the other side. Guess that's 1950. 1950 newtons times meters. Okay, so then I'll divide both sides by that big nasty parentheses thing. So I'll divide by, in parentheses, 5 plus 10 sine 63.435 close parentheses equals 139.84 newtons. Okay, note that with tensions, like if you get a negative number for a tension, that means you assume the wrong direction for a tension. There's something really wrong, okay? Because ropes can't push, okay? So you either assumed that the rope was pushing and it ended up as pulling, or you made some other math error, or, you know, who knows really what else could have happened, okay? So anyway, so I'm gonna go back into this initial equation up here. So I'll go to fx. It doesn't really matter which one I do, but I'll go to fx first and I'll say, okay, well, we've got negative ax minus, well, I guess I could make it equals, bring it over to the other side, t 139.84 newtons cosine 63.435 degrees. So that's like some of my worst handwriting ever. Oh, not equals 0. Oh, okay. So then we'll say ax equals negative. Okay, 139.84 cosine 63.435. Okay, so we get 62.538. Okay, that negative sign means I chose the wrong direction. So ax is in fact to the right. Okay, so I'm going to show you in a second how you would, you know, so how you report your answer. Never report your answer like this. Okay, that's a no-no. Okay, and then let's just go ahead and we'll do this equation right down here. I'll say negative ay plus t 139.84 newtons, and I'm going to pull it out. 1 plus sine 63.435 degrees minus 150 newtons equals 0. Okay, so we go, let's see, 1 plus sine 63.435. Okay, take that, multiply times 139.84. Subtract 150. Okay, bring to the other side, blah, blah, blah. AY equals 114.92. Okay. So, so what this all means is that, you know, this one was, so AX was drawn the wrong way. So AX should look like this. It should be like this. And AY was, because it ended up with a positive sign, was drawn the correct way. So it should be like this. Okay. So in this case, I asked for the vector of A. So we should go ahead and get that vector. And the way that we would normally do that is in polar coordinates. So, and I'm going to do this quickly because at this point you guys should know that A, the magnitude of A then is what, 62.538 squared plus 114.92 squared, square root. And the direction theta equals, well, let's see, we're talking about a triangle that's what, 62.538 this way and 114.92 that way. So our triangle, and I know I'm doing this quick and sloppy. So this is going to be the inverse tangent of the opposite, which is 114.92 over 62.538. Okay. And so that's how we would solve this. And so our final answer for A would be, let's see here. I might get out of here. Okay, I really should like write a little program to do this Pythagorean theorem. I bet there's probably one built into the calculator. So A equals 130.83 newtons at an angle. In this case, it's a negative angle, like that. Inverse tan 114.92 divided by 62.538 close parentheses equals 61.446 degrees. And because I only want 3 sig figs, it'd be 131 newtons at an angle of 61.5 degrees. Okay. If I just wanted AX or AY, AX would have been would be 62.5 that way. And AY would have been 114 or 115, excuse me, 3 sig figs down. Okay, so yeah. Any questions?
Yeah, I got 2 questions.
Okay.
So when you got AX equals a negative, you said that made you know you got the signs wrong. How was that? Because like I would have, if this was on a test, I would have just wrote negative 62 and called it good.
Right. So when I did my initial free body diagram, the left-hand side, I drew AX this way.
Uh-huh.
So based on that, I assumed it was going to the left right here. I think that was the only place it showed up. Yeah, it's the only place AX showed up. So I assumed it went to the left. So when I got a negative sign, that means that this was like, basically it's going this way, negative 62. So going to the left, negative 62 is the same as going to the right, a positive 62.
Okay, cool. That makes
Okay.
sense.
Okay.
And then my next question is, how do you know that the angle of A is below the x-axis like that?
Oh, because, so I had, so my force was, so it was 62 in this direction, and it was 114 in this direction,
Oh, I see. Yeah, okay. Yeah, totally.
or 115 or whatever. Okay, good questions.
But how do you know that? Like I don't, just from looking at it, or just
Well, so
when
this
you
is-
set the-
So this is so this number right here, this is the x direction, right? And if I know it's to the right, because I assumed it was to the left, but I got a negative sign, so that means it's actually to the right. Okay, so I got 62 to the right. Or 60,
wait,
whatever.
so you there's no way you could assume, like you can't look at the free body diagram or the picture and just know which way it's gonna go.
I might be able to do it. I don't know that you would be able to do that yet. So no, not really.
Oh, so at a pin, does it go to? Because I mean, if you would have assumed that AX went to the right and you had AX positive, you would have came out with a positive answer.
Yeah, so if you assumed AX goes to the left, you're gonna get a negative number, and it actually went to the right. If you assumed AX went to the right, you would solve and you get a positive number, and that would tell you AX was to the right. So no matter which way you assume, you will end up with the same answer. Okay, and then for the AY, we assumed it went down, and we got a positive number. And so that means we were correct, it was going down.
Oh, okay.
Okay, so
So
that's
if
how I
you
knew
get a
this was
negative
down.
number, then that means your assumption was wrong.
Yeah, if you get a negative number, your assumption was wrong, exactly.
Okay, I understand.
Okay, and I think, I probably won't work many like this again. It's just, for me, I usually like to do them, what's the word? you know, I always just like to assume they're positive, even when I know, even when I'm like 99.9% sure, you know, I just like to assume they're positive, because if I assume they're positive, then the negative number means I'm wrong. And in this case, being wrong means it's also that it's going to the left or it's going down. And so, you know, you can do it however you want. You know, a lot of teachers will tell you to just try to guess the direction. My teacher, when I was taught this in 1997 or whatever year, she was very much like, you know, just make them positive. I think that that's a good strategy, but it's not the only strategy. So sometimes you just got to find something that works for you, you know? So, you know, I like thinking about a problem before I work it, because it kind of gives me some intuition about what's going on instead of just plugging in numbers. So at the very least, I think it would be good to stare at the question and say to yourself, okay, do I think this thing's going to be positive or negative? Just so you get some intuition. That would be the ideal to me. But mathematically, it's always easiest to just assume positive.
I have a question about A of X. You said leaving the answer like this is no. Does that mean like leaving it in the negative, or did you mean something else?
Yeah, leaving it in the negative.
Okay, thank you.
Yeah. And so you should always give it a positive and give it a direction. So what most teachers do for AX and AY, what most professors, what I see most of my students who have taken from other professors, so I'm assuming that's what most other professors do, is they'll have you do it like this. With AX and AY, just give you an arrow. Because what they want to know is do you know what this negative number means? You know, not just can you do a bunch of like algebra and come out with a negative number. It's like, you know, can you make sense of it? Okay. We're just about out of time, so I'm not going to be able to do my last problem. Just make a note here real quick. If there were an applied moment, okay, like if somebody came up to this thing and they applied a moment, like they came up to this original thing and they said, you know what, right here, I'm going to apply a moment. Let's make it a negative moment. Like this, right? And I'm going to call that moment M. I don't know. Let's not give it a letter. Let's give it a value. Okay. 100 newtons times meters. Okay. Let's suppose that was in the initial statement. Somebody was applying 100 newtons times meters. And the interesting thing about these applied moments is it doesn't matter where they're applied. All that matters in this case is it's in the Z direction. Okay. Meaning, you know, if you take your pen and you just kind of like put it down at point C, you can see that this thing, sorry, I'm having trouble balancing it. And so it's drawing everywhere. But you can see that this, like if you put your pen down on C, you can see that this moment is going around that, it's going around that pen. Anyway, the only way that would change this is that's a negative moment. And so in our moment equation, we would add another term of negative 100 newtons times meters. Okay, so it makes the algebra, you know, the tiniest bit, you know, it's like one more term, but it doesn't make anything more difficult. Okay, I meant to work one of those today, but we ran out of time. I will work it next class, but I think next class is the test, right? Yeah. So any questions about tests, what it covers, how to study, anything like that? I guess I should have done that at the beginning.
And you said you'll send an email out this weekend with more details.
Yeah, I'm going to give you details about what to bring, where to go, et cetera, et cetera. If we have to do the exam online, oh, by the way, there's no way I'm going to get a classroom for this class, so we are going to be online. But if I can, in general, not for the test will be in person. If I can get a class.
Thank God.
Okay, right. So if I can't get a classroom for the test, which is still a possibility, I'm still kind of trying to work that out. But if I can't get one, then you'll have to have a mirror behind your desk so I can see your screen. You know, obviously that's not the ideal situation. I'm trying to get the auditorium. It looks like I've got a pretty good chance of getting the auditorium, so everybody will be able to space and spread out and, you know, do whatever. But yeah, I will send you full instructions, blah, blah, blah. But as far as studying for the exams, anybody have any questions? So, but don't forget to check your email. But anybody have any questions about studying for it or anything like that?
for some of the details that you're gonna be sending out this weekend over an email, are you gonna be including the chapters covered?
No, all of that is in Moodle. So if you go in Moodle and you look at hold on. Stop share screen. I mean, I must be saying this confusingly because this seems to be the most question. So clearly something's missing. Let's see here, Moodle. Okay, it's everything up to, but not including, okay, let's see. All right, let's see. Okay, so it's everything up to September 25th.
Okay, thank you.
Okay, so we could highlight that and we could say all of this. So it's homework up to C4 and homework 4. Which I guess I'll have to, which I guess I need a grade. I also need a grade homework 1. I got a lot of grading to do. So you'll get all that too. I'm really behind. Any other questions?
And doesn't reflect here, but you moved C4 back, right? You had said last class.
Oh, I moved it back till Sunday, right?
Correct.
Yeah,
So I'll
so,
clarify.
yeah.
So just homework 4 is due tonight.
No, so-
Yeah, I guess homework 4 is due tonight. Yeah. Oh, wait, no, homework 4 is also due on Sunday. Sorry, homework 4 is also due on Sunday.
Okay, that's great because I have a test today, so I'm like trying to study for that.
Yeah. Like I say, like, I'm not trying to stress you guys out about the homework, but clearly a lot of you guys are stressed out about it. So please, let's focus on what you can learn from the homework and not about the grades for the homework. It's easy to say from my end. I can say, and I firmly believe this, that the reason I was able to get, one of the reasons I was able to get a PhD, I think, is because I went up to the professor after class when I was working on my master's degree. And, I felt like there was an error in the key or whatever. And I was like, I think that this should be a negative sign or whatever. And, I got like a 9 out of 10 or an 8 out of 10 on the homework. Like my grade was fine on the homework. And he looked at it and he was like, yeah, you're right. And then I could see this look of like aggravation on his, on his face. And I was like, look, I don't care about the point. I just wanted to know that I got it right. He's like, okay. And I think that right there, like for him, like, I mean, I wasn't trying to, kiss butt or anything, but I think for him, like in the long shot, in the long term, he ended up being my advisor for a PhD. And I think on some level, like that kind of told him like, oh, this guy is like just trying to learn, I mean, the goal, and I'm not saying the goal should be to impress me, but the goal should always be to try to learn. And that's actually why I really enjoyed y'all's questions today. You guys have asked really great questions. And thank you for that. Anything else? Go ahead, Brandon. I interrupted you.
Oh yeah, I was just I retook all of your exams you posted on Moodle, so like those were really helpful because they like, I mean, you reuse like the same 4 questions on like on your old exams, so I have a pretty good idea what might be on the exam now.
Right. So I would expect a little bit of variety. Like I'll probably pop something in or pop something out, but it won't be different in scope or in kind of like, what we're aiming for. So, so.
Although I do think you are a bit tricky with your questions. Like there's some stuff like, I don't know, there's some stuff that is like unusual. Like I don't know, but I had to look at the answer key for a few of them because I was like, what is like going on for, I mean, you can solve them like halfway, but then you have to, like, you don't know what to do. But I mean, now I do. So
Okay. Well, I didn't mean to be tricky. I'd be interested actually if you would tell me what you thought was tricky, but not right now because we're in class and
yeah, okay.
some people are trying to like glean any last little bit of information before they can go off to their next class. I know how it is. I remember. Anyway, so if there's no other questions, I will see you guys on Tuesday, hopefully in the auditorium.
Bye.
All right. Bye. And
Thank you. Have a good weekend.
great class. Yeah, have a great weekend.
Have a good one.
Don't study too much. Study just the right amount. How's that? Okay, I guess we're done here. And oh, we're recording, aren't we? Let's stop recording first.